Alright, so now that we have a little bit of what an amino acid is, its structure, kind of its side chains, and what the properties are, let's go a little bit into the synthesis of it. This is really more of a true organic biochemistry technique. A lot of detail here, a lot of potential in the scientific realm. However, for MCAT purposes, we'll keep it fairly light and fairly simple and straightforward. One of the ways we are able to make amino acids and synthesize them in the lab is the Gabriel malonic ester synthesis. So that's Gabriel malonic ester. It's one of the starting materials we're going to use. Amino acid synthesis. So again, the name kind of says a little bit about everything it is we're trying to do. It's a specific method, and one of the starting materials we're going to have are making amino acids. This is one way. So again, the important thing, do not get bogged down in the details of what this mechanism is. You're not writing mechanisms, you're only selecting pictures on the MCAT. So it's very, very important just to think big picture here. The details will be in the passage, the details will be in the pictures. You're just trying to identify what's going on here. So we'll keep it pretty light. So, the starting material though, you should have a good idea. It's a very easy to identify molecule, super long, difficult sounding name, I can't even say it, malonic ester. So, this looks like phenyl group, which you're used to. And then we have the actual ester part here. And this is the molecule we're looking at. And then the more common, let's see, C-O-O-E-T, C-O-O-E-T, and a couple H, and the H coming off here. This is the actual ester part that we see. It's got the two esters. So if you think about this back from some of our earlier discussions, just to give you a little flashback. We've seen and dealt with this material several times in the past. We talked about specifically how it has the potential to be a very, very, very good enolate. There's that alpha position wedged in between two carbonyls. We know that these alpha hydrogens that come off this carbon are acidic, and when we use a base to go with them, we form that enolate that we spent a lot of time talking about. Very good enolate, which makes a very good nucleophile, which allows us to run into all kinds of good things. So this is kind of the reaction you're used to. It's a more simplified version, so let's think about the simplified version of this while we discuss a more complicated version. So again, remember, think big picture here. The big picture here is here's our ester we're playing with. Here's an alpha hydrogen that's acidic. All we need is some kind of base. Something like as simple as methoxide, for instance. We use a base like methoxide. In doing so, that base will remove this acidic alpha proton that we have here. So that when we go into our next picture, we have in and all that stuff attached to it. I'm going to just draw the first little part of the N. We put a squiggly line to represent the rest of that. Now we have a carbon. Still have that C-O-O-E-T up there, C-O-O-E-T here. Now we have a minus charge. There's our enolate. Enolate, as we recall, very, very, very good nucleophile, looking to run into anything. And as you'll recall when we were doing these types of reactions, it's basically an SN2 reaction at this point. This takes on a very similar shape. What we'll see at the end product here is what our amino acid will become. This will be the carbon, the carbonyl end of our amino acid. This will be the amino end of our amino acid. These right here will be our carbon chains. This one will be a carboxylic acid. One will turn into the CH2 from the structure we previously saw from amino acids. So really now what we're trying to do is make our R side chain. So the R group, recall, is what makes every amino acid different from one another. Depending on what you want to do, it's a very simple SN2 reaction here. At this point, we would introduce the next part of our reaction. Let's say we were just going to put on an ethyl group. using an SN2 reaction, we'll make it the most simple way possible, ethyl bromide, for instance. We know an SN2 reaction likes to hit into those primary carbons with excellent leaving groups. So it fulfills the requirements of the SN2 reaction, which is the big important reaction we've already talked about. We have a good nucleophile, a great position for it to hit into, and a great leaving group to come off. And I'll try to match the colors here, that way you can follow what's going on. So in our next diagram down, we have that carbon still attached to all this side stuff. Still attached to the end. That's going to come off shortly. And all that stuff. Now what we've formed is a bond here. Where it's now, if this was carbon 1 and carbon 2, we now have carbon 1 and carbon 2 with their attachments, which would be the H's. So that's where we get that. We have a final step, and I shouldn't say final, but close to the end of the step, where we start to clean this up and make it look like the amino acid. The next part is the hydrolysis. So we actually have acid hydrologist, and what it does is really works on cleaning up this to make it look like the amino acid we're used to seeing. So how you'll see this written is our next step, which will keep it blue. The next step to this reaction is simply using dilute acid, H+, in water. And this is where we have, just think of it as a cleanup. And again, we're going to think broad picture here and broad scope of everything that's going on. So this is the cleanup step, where our nitrogen, can't find your mark, that works. Nitrogen becomes a familiar NH3 amino side with a positive charge. The carbon, which is that central carbon, now we have an interesting thing that goes on here. After the acid hydrolysis step, one of the carbons turns into the carboxylic acid, right there, so that's the carboxylic N. We still have what we just made and what we just added on, this 2-carbon molecule right here, carbon, carbon, and the appropriate number of H's. Doesn't bother those. And for our final one down at the bottom, this is where we get an H. So here, again, we're trying to think big picture with the Gabriel malonic ester amino acid synthesis. You've seen a very similar reaction before. The big takeaway points here is just a specific reaction in the grand scheme of all the reactions we're kind of learning. It starts with a very specific material that you'll recognize. They'll probably point out even on the MCAT. And what it goes through is a reaction we're very used to already seeing. We have that alpha carbon that we're used to dealing with its very acidic alpha hydrogen. We know this position is very acidic. We use a base, any base, like we used here, methoxide, to abstract that alpha proton, form the enolate. That enolate then undergoes a nucleophilic reaction, in this case an SN2 reaction, into whatever we want the R side chain, that synthesis part, that amino acid we're trying to synthesize. That's what it's running into, doing an SN2 reaction, and then it goes through acid hydrolysis, which is our cleanup step, is how we want to think of it, to make it look like the form of the amino acid we're used to seeing. That amino end with the positive end, the carboxylic end, the central carbon, and then that R group that we're adding on here. So that's one of the ways we can do an amino acid synthesis.